All right, ladies and gentlemen, last one of chapter 1. So, find the limit of the function f of x equals the greatest integer of x as x approaches 0 from the left and right side. So, the limit as x would approach 0 from the left of your greatest integer function. Well, as we go from 0 from the left. So, if we look at the graph of the greatest integer function, it's doing one of these things. So from 0 to the left side, if we follow it down, we're going to be down here at -1. However, the limit as x approaches 0 from the right side of our greatest integer function, well, on the right side of it here, we're up here at 0. So there we have the left and the right side functions. Now, in the past, we said that, hey, if it goes unbounded, the limit does not exist. Well, we're kind of going to amend that a little bit and say, hey, if that limit doesn't exist, if that's unbounded, we really know what it's going towards. Unbounded means it's going to infinity. So what we're going to have here is an infinite limit. So if we put this into a graphing calculator, you would see, and I can do that quick. So in the y equals, I'm putting 3 divide and then parentheses x minus 2 so that it knows that's the entire bottom. And if I hit graph, here's what our graph does. So as we get closer and closer to 2 from the right side, we're going to shoot up to infinity. As we come from the left side, we're going to shoot down to -infinity. And so we can find actual infinite limits, which just says that, hey, there's going to be a point we're going to realize that, hey, it's going to infinity or going to -infinity. And so those would be infinite limits. So even though it's not going to a specific number that we can't say, hey, this is the limit, we know it's going to infinity. So in a roundabout way, we kind of know what it is. We can't specifically say, but we know it's going to infinity. So as a summary here, it doesn't mean the limit exists. It's just that the limit fails to exist because it's unbounded, because we know it goes to infinity. So it's still technically not the limit, but we know what it's doing. Trying to think of a good analogy of we'll just move on. We'll save analogies for later. So we can use the graphs to determine the limit as x approaches 1 from both sides. So here from the left, we're going to -infinity. From the right, we're going to infinity. On this one, both sides, we're going to infinity. Here, the left goes to infinity, the right goes to -infinity, or they both go to -infinity. So just some different examples of where things are going to go. Now, if you notice there, we have that dashed line. Well, infinite limits are going to involve vertical asymptotes. That dashed line is a vertical asymptote. So vertical asymptote is what causes the bottom basically to be 0. So these infinite limits are going to occur wherever the bottom cannot equal 0. Whatever x will cause the bottom to be 0, which is what we can't have, we'll avoid. So it's a vertical asymptote. So, looking at these here, which we have another theorem with vertical asymptotes that just says that, hey, whatever makes the bottom equal 0 is what's going to cause the vertical asymptote here. So, this one here, what would cause it to be 0? Well, it's going to happen at x equaling -1 is where your vertical asymptote is going to happen. So that's your vertical asymptote for this one. This one factors out to be x minus 1 x plus 1 since it's a difference of squares. So here your vertical asymptote will happen at both 1 and negative 1. Now with cotangent, cotangent's a little bit harder to do. If we wrote this as cosine of x over sine of x, we would look at, well, where can x, or can sine not, where would sine equal 0? Well, sine is going to equal 0 when x equals any multiple of pi. So this is where the vertical asymptotes would take place in these. So here we're looking for what's going to cause the bottom to be 0. Well, with cotangent, again, harder to see, so we rewrite it in terms of cosine and sine. So it makes it a little easier to go, okay, well, we just don't want sine to be 0. Well, using the unit circle, you would see that, hey, at 0, at pi, at 2 pi, at 3 pi, at 4 pi, that's when sine equals 0. Here, we may have to factor it out. So here it's difference of squares goes to x minus 1, x plus 1, so we get 2 vertical asymptotes. Here, if we put 1 in, 1 minus 1 is 0, negative 1 plus 1 is 0, so that's our 2 vertical asymptotes. So determine all vertical asymptotes of this graph. So the first thing you need to do is this. Factor the top, factor the bottom. So the top, 2 sets of parentheses. X squared would be x and x. 8 is a minus, so 1 is plus, 1 is minus. And the middle is positive, so the bigger number has to be positive. So a difference of 2 for factors of 8. Well, 4 and 2. Bottom, this is a difference of squares. So this is going to go to x plus 2, x minus 2. So right now our candidates for asymptotes are when x is negative 2 and x is 2. However, for an asymptote to exist, it can't be removable. So if you think back to, I believe it, well, was the last lesson? A previous lesson, we'll go that way, where we had the removable and non-removable discontinuity. Yeah, last lesson. Here, the plus 2 wouldn't cancel out with anything. The x minus 2, though, would. So that means that this is not an asymptote. This, because it was removable, is a whole. So here it's going to be like line, going to be a spot, and then continue on. So it's continuous everywhere except for that one spot, and it's going to be a hole. We're at negative 2, we're going to have a vertical asymptote. All right. So if you can cancel it out, it's just a hole. It's not a vertical asymptote. If you cannot cancel it out, then it is a vertical asymptote. So that was stuff we talked about last year in advanced math, but just kind of a refresher there. So here, if we want to find the limits of each of these, well, we know that at 1, we're going to get 0 on either one. So we don't necessarily, or we can't necessarily just put that in and get it. However, we're going to look at, can we pull anything out of the top? Well, actually, no, we really can't. Because if we pull an x out, we'll still have x minus 3, which doesn't cancel anything with the bottom. So we know we're going to have a vertical asymptote at both of these when x equals 1. So that's why we're looking for, what are we doing from either side? Well, on the left side, if we're less than 1, that means this bottom would be less than 1, and so we're going to take away more than what we have, and so we're going to have a negative here on the bottom. Up top, we'd square it, minus 3 times 1. Well, for less than 1, we're going to get smaller than 1, and we're going to be taking away 3, so we're going to take away more than what we have again. And so we're going to have negative over negative, which goes to be a positive then. But we're going to have a bigger number over a small number. Big over small means infinity. So we have a big number broken up into many, many tiny, tiny pieces, which makes even more pieces, which makes it go to infinity. So the limit here as x goes to 1 from the left side is going to equal infinity. Now, on this one up here, from the right side, we're going to be bigger than 1. So we're subtracting less than what we have, so it's positive down here. Up here, though, we're still going to be close to 1 and taking 3 away, and so we're going to have negative, which means we're going to end up with a negative answer. Now, same thing, we're going to have big over small, because if we're close to 1, we're going to have a little tiny number on the bottom. Here we're still going to have a small number minus 3, which is going to end up being big over small, and so we end up with the limit as x approaches 1 from the right side of a negative infinity. So, some properties of limits. So if we have one function that goes to infinity and another function that goes to a specific limit, if we add or subtract them, it's going to go to infinity. So think of it, it's like if this is going to infinity and this is going to 1, infinity plus 1 is still infinity. Or if we have it, we're going to infinity and we take 1 away, we're still going to infinity. If we multiply them, we're going to infinity. If the limit's less than 0, though, so if it was negative, say, and negative 1, so now our limits would be a negative infinity. Now, if we divide these out, a small over a big is going to go to 0. So small over big in this case. So big over small goes to infinity, but small over big goes to 0. So keep that in mind when you're working through these. If you end up with a small number on top and a big number on the bottom, going to go to 0. If we end up with a big number on top, small on the bottom, then we're going to infinity. So big over small, infinity, small over big, 0. Same thing goes for one side limits if we're going to infinity in that case. So determine the following limits. Well, first one here, I'm finding the limit as x goes to 0 of 1 plus 1 over x squared. Well, I can't put 0 in because I'm going to have 1 over 0, which is bad. So if we look at the left and right side, so the limit as x goes to 0 from the left. So from the left side, we'd have a negative number, but it's squared, but it'd be small. 1 is going to seem like a big, so 1 plus a big over small. This is going to be infinity. 1 plus infinity, still infinity. If we look at it from the right side, again, right side, so positive number squared is still positive, but it'd be a small number, so like 0.1 squared is 0.01. We're going to have a small number and compared to 1. So again, that's going to be infinity, and 1 plus infinity is infinity. So the overall limit as x goes to 0 is infinity on this one. Here specifically, we're going to look from the left side. Well, if we look at the top part, from the left side of 1 is smaller than 1, but still positive, so 1 squared roughly would be 1 plus 1. We're going to get a number up top. Well, if we put actually 1 in there, yeah, 1 plus 1, we get 2. So the limit as x approaches 1 from the left side of the x squared plus 1 is 1. And the limit as x approaches 1 from the left side of the bottom now, cosine of pi over x. Well, in this case, pi now at 1, so when x is 1, well, 1 times pi is pi. Cosine at pi. So when we're on the left side, cosine is the x, we would be at negative 1. Wait, I'm doing cosine. This is a typo. This is supposed to be cotangent. That's why it's throwing me off. I'm looking at my notes like, hey, this should go to negative infinity. Why is it going to negative 1? Well, again, cotangent is equal to cosine over sine of x. So at pi, this is where we're going. So at pi, sine is 0. So the closer we get to it, the closer we're going to get to 0, which means it's going to be a big over small situation. And so it's going to go to infinity. Now, because we're on the left side, we're going to negative infinity, which was negative big over here. To make it a negative infinity, sorry. So now the overall limit, as x goes to 1 from the left side, well, up top, we're going to 2. The bottom, we're going to negative infinity, which is small over big, which equals 0. Now, as far as cotangent goes, now we're just on top. So I'm going to move C down here. The limit as x approaches 0 from the right side of 3 cotangent of x. Okay, so at 0, again, cotangent is cosine of x over sine of x. Well, at 0, again, sine, it's going to be 0. Cosine is going to be 1. So we're going to have big over small. So this will go towards 0. This will go towards 1. Big over small is infinity. And we're from the right side of 0. So the right side using your circle, you're both positive. Sine and cosine, both x and the y, are positive on the right side towards 0. So this is going to be infinity. Because technically cosine, or the limit of 3 would be 3, but cotangent. So let's do this. So if we break these up, we'd have 3 times infinity, which the whole thing would go to infinity then, to use those properties. So that's the last one of this lesson. If you have questions, comments, concerns, please pan me, email me, send me a message. Let me try to explain this more to you. I know watching a video isn't always the easiest, but hopefully it helps. Remember, you can always pause if you need to write stuff down. You can always rewind if you need to hear something again. Otherwise, until next time, we'll talk to you later.